Ladies and gentlemen, today I'll talk about our paper LHF, a new archive-based approach to accelerate massive small files access performance in HDFS. We are from School of Computer Science, Beijing Institute of Technology, China. I'll talk about our paper from four aspects: background information, inner Hessian fire, experiment evolution, and conclusions. First, I'll talk about background information. Why do we need to solve small file problem? In the contemporary era of ABC, AI, big data, cloud computing, a huge amount of data is being generated and this data has to be stored, processed, and analyzed. As a widely used cloud storage platform, Hadoop has a feature of open source low cost, high fault tolerance, and scalability. Practically, the production of small files has become increasingly common, and the amount of data is too large to be stored and processed by using local file systems in many applications. Moreover, small files have to be processed along with big files. HDFS consists of one lam node as the master and a group of data nodes as neighbors. Lam nodes is responsible for managing the metadata for the whole file system. Presently, there is no existing standard and generic file system that is specified designed for storing, handling, and analyzing small files. So it is necessary for us to solve small files problems on HDFS. What is small files problem? First, name node performance degradation. The second is high storing time. The third, MapReduce performance problems. Last but not least, name node memory consumption. There are some solutions provided by HDFS, such as HAR, sequence file, and mapfile. Hadoop Archive or HAR is an archiving tool that efficiently puts small files into HDFS blocks. It can pack multi-small files into one HAR, which allows the file to be transparent while reducing the use of lamnode's memory. However, however, HAR has some drawbacks. First, once created, archives cannot be changed. To add or remove files inside, you must recreate the archive. Second, when accessing the HAR files, it requires two index file read operations as well as one state file read operations, which are less efficient than reading files from HDFS. Sequence file, which stores the data in the form of binary key value pairs, is used as a storage container for small files. In this state structure, file name is stored as the key, and the file content is stored as the value. Sequence files also present several disadvantages. For a particular key, it doesn't have a mechanism for updates and delete operations. It only supports the append method, and secondly, this approach has no access efficiency as it takes a quite long time to make a sequence file. If a user needs to look up for a particular key, it is required to read the sequence file from the beginning of this sequence file. A map file which is composed of two files, an index file and a date file, is sorted sequence file. It maintains the index file to store keys location information to allow lookup of date file by key. Map file facilitates to look up for a key without having to read the full files. However, it can't provide flexible API for applications as only append method is supported for a particular key. In other words, not every key can be appended to a created map file because it must keep all the keys in order. Furthermore, while reading a file from map file, we need to search the index file, address the disk once, and scan with 20 and 128 entries at most. By default, the less key stored for the same small file sets, the more entries are required to be scanned and compared with the target key. What is linear hashing? Linear hashing is one type of dynamic hashing that supports dynamically expand the hash table by adding one bucket at a time. This single bucket expansion can efficiently control the collision chain. The cost of a hash table extension does not happen at all at once, but throughout each hash table insert operation. It consists of a hash function, h data bucket, a bucket array A, and met information. The data bucket is made up of data blocks, and the met information includes the hash level I, the number of dates buckets N, the number of records R, and a fixed fraction P is the list up bound of R divided N. The second aspect is linear hashing file, LHF. The basic idea of our proposed approach includes two steps: merging small files into large files and reduce quantity of files and optimize name load memory consumption. Storing these small files metadata in our index system based on linear hashing principle, thus allow us extending the function of file management, such as append additional files to the existing archive file, delete files from the archive files, and so on. To solve the small files problem, we merge them into large files on HDFS and use linear hashing principle to organize these files' index information in several small index files. From this picture, we can see file filtering criteria. Model classify files into three categories according to the file size: large files, common small files, and ultra small files. Large small files are directly uploaded to HDFS. Common small files and ultra small files are sent to the file merged model to build the merged file, and then the merged file and the index files are uploaded to HDFS. In our design, the file filtering criteria model will classify files into three categories: large files, whose size are larger than HDFS default block size, 128 MB. They will be uploaded to HDFS. Ultra small files, whose size are smaller than predefined value, in our case 1 KB. They will be processed by the file merging model and stored it in the index files directly. Common small files whose size are between the predefined value and the default HTML block size. They will be processed by file merging mode and merged into BDS path files. The features shows the proposed structure of the archive file. The archive file consists of two parts: the index part and the data part. The data part stores the content of common small files, and the index part stores the ultra small files contents and the index information of all files in this archive. Common small files are and ultra small files are handled differently in the file merging model. In case of common small files, the file container is appended to the data parts and the information like their size, the location of small files in the data part file, and so on are used to build an index record that is inserted to the index part. In case of ultra-small file, we directly write the contents of the file to the appropriate buckets of the index part using linear hashing algorithm. The data part consists of a sequence of part files. During the merging process, if the remaining space of the part file is smaller than the small file size, we create a new part file to continue writing new small files content. As a result, a small file's content is only in one data part file. Since common small files and ultra-small files are handled differently, the information stored in the linear hashing also different. First page is stores common small files index information, and the second picture describes the information of ultra-small files index index. To increase access performance, the LHF use single index level instead of using master index approach as in HAR. LHF organizes index parts as linear hashing, where the index records are split into several index files that represent the hashing buckets. Each bucket is stored as a HDFS file, and the name of the bucket file is specified as the bucket label for easy locating. As the number of records in index files increases, the buckets are split according to linear hashing split policy. After all the files are merged, the contents of each bucket in linear hashing are sorted by file name and then written to HDFS. The linear hashing we use to store index records is described as follows, and we define some parameters like n, the number of buckets. The buckets are numbered from 0 to 1 minus n minus 1. Level, the number of bits used in file name hashing value to decide in which bucket to store its information. It is also the number of bits necessary to represent n minus 1. Gamma, defined as total number of records in all buckets. Alpha, the average policy defined for each bucket. Load factor, the fill rate of all index files, and is calculated using uh, this this formulation. The split policy. It is a policy that we define that will allow us to create a new bucket by calling the split operation when the available buckets are getting filled. The split operations are done in round robin. They serve to extend the number of index files when existing index files are reaching their maximum capacity. For example, uh, in this picture, there's two buckets and at the beginning. Now, um, we will add a new bucket. In this example, we have two to three buckets, 0, 1, 2, and then n equals 3, label equals 2, because last bucket label is 2 equals um, 1, 0 in binary. We need 2 bits to represent 2. Actually, the label is 2 to find the corresponding bucket at label -1 position. We just take the corresponding binary represent our new bucket position without first bit. The new bucket position is 2, 1, 0 in binary of the corresponding bucket at level 1 and level -1 is at position 0. To access files in the merged file, our archiving program uses the hashing function to calculate the linear hashing code from these files for them. With linear hashing calculation module, we locate the index file containing the information of this file. Then we look up the file information in index file using a binary search method. With the acquired information, our program will extract the file identifier to determine this file is a common small file or an ultra small file. If it is a common small file, locate the date part file and seek the date part file to the starting position and then reading file state. If it is an ultra small file, we got the file content within the information obtained directly. Appending small files. The process of appending small files is similar to merging small files. Certainly, there are some differences. We ought to read all the index part files on HDFS to build a linear hashing in the client's memory. During the appending process, common small files content has to be written into to the last created part file that is smaller than the defined maximum size value, otherwise written to a new part file. Next, I will show you the experiment evolution. The experimental environment is built on a class of 4 nodes. One node serves as name node, and the other 3 nodes act as data nodes. Each of them has 4 process and 4 GB memories. The operating system is CentOS 6.6. The GDK version is 1.8.0 and the Hadoop version is 2.6.5. The number of replics is set to 3 and the HDFS block size is 128 MB. The files we use in experiments include text files, web page files, and images. To test the performance of LHF comprehensively, we utilize different kinds of file sets to do the experiment. First kind of file sets is text file sets, which contains 20,000 40,000, 60,000, and 80,000 files respectively. The total size of file set is up to 128, 288 MB, and the file size range from 250 B and 100 to 160 KB, which means many ultra-small files in this data set. The second type of file set is about 1.5 GB and contains about 20,000 files whose size range from 20 KB to 30 MB, which means all files are common small files in this data set. We present environment results of LHF comparing to native HDF, HAR, and MapFire to evaluate the performance of accessing small files. We perform the read operation directly from HDF, HAR, MapFire, and our LHF on first file set and the second file set, which are repeated 5 times. For first file set, we read part of the file set and the whole file set. When reading part of the file set, each time is tested with the same 2,000, 4,000, 6,000, 8,000, 10,000 random files with different methods respectively. When reading all the files in the multiplier, our LHF still perform the best. We also calculate the throughput rates of reading entry file sets and evaluate the time spent on creating an archive file to store the file sets and the memory usage in name of storing small file. To avoid the coincidence that our LHF provide good performance tested by only the first kinds of small file sets, we further use the second kind of file set in which file size range from 20 KB to 30 MB, so there is no ultra small files. The reading performance is shown in the next figure. The last part is conclusion. In our method, small files problem of HDF is solved, and the files to be merged don't need to be sorted, which makes appending additional files to existing merged files possible. For random file access, you can use a file name to locate the bucket file in the index, which only needs one-time hashing computation. When reading the file content, reading the corresponding content according to the index information to the specified location of the specified file without having to find the corresponding content in the data file like map file. Compared with multi-merged files, appending additional files to existing merged file can make full use of data block, avoiding the case of that a small number of files also occupying a merged file and a corresponding index file to some extent and elevates the memory pressure of the name node. Okay, that's all. Thank you.